for your presentation. So it's with great pleasure that I welcome Rachel to the virtual European Colloquium on Theoretical Quantitative Geography. It's the last keynote lecture, which is great. We had a great program so far and people came in different ways, but with very good attendance. And so we'll finish on a Friday afternoon the best way possible with your talk. Professor Rachel Franklin is Professor of Geographical Analysis in the Center for Urban and Regional Development Science. Did I get it right? Perhaps not, but in Newcastle University. And will give us a much anticipated talk to close the colloquium this year. Rachel, the floor is yours. You take your time, I assume. Then we have some discussions, and if it's too long, I'll waive it. So take your time.
Okay, well, I'm aiming to talk for, I think, maybe about 45 minutes, and hopefully that leaves some time for discussion afterwards. Let me just find the screen that I want. Okay. Is that good?
Good, that's good. It's here.
Someone? Okay. All right. Thank you so much for having me today. I'm so sorry about my Zoom challenges. You'd think a year and a half or 2 years into this, we'd be experts, but apparently not. I'm actually in the US at the moment, in the middle of nowhere on the grid, or off the grid, I should say. So hopefully my internet connection doesn't stall out. So if there are any problems, somebody just speak up and let me know, and I'll slow down or go back, whatever works. But today I'm really pleased to talk about a project that's been ongoing really for the last 3 years, but has been paused for about a year because of the pandemic, and just restarted about 6 months ago with sort of a turnover in team members. So I'm sort of excited to tell you about where we've gotten so far and where we'd like to get in the remaining time that we have left on this project. And this is a project about spatial inequality, but in particular, smart city technologies and sensor networks in the urban landscape. And there we go. And this is a big team. And it has changed a little bit over time, but this is a project funded by the Alan Turing Institute, and it's funded some research software engineers. So Kate Court at Newcastle University and a data scientist, Jack Roberts at Turing, and then 2 postdoctoral associates. One is Kate Robinson, who's now a lecturer at Liverpool, and now Iman Zeid, who's been on the project for the last 6 months. And so everything I'm going to talk about today is really a team effort. I think you'll see that there are lots of moving parts, and that I really have relied on the expertise from lots of different domains to get us as far as we've gotten. Right, so this project, which benefited from seed funding from the Turing Institute starting in, I think, autumn of 2018, was really interested in identifying and improving inequalities in cities, and in particular, the ways in which spatial demography and sensor technologies interact or interface with each other. All right. And so just to get us going, right, before we start talking about the particularities of sensor networks and smart cities, I think it's really helpful to just think a little bit about what we mean by inequality. And it means lots of things to lots of different people. But one thing, of course, is that it's structural. And thinking about this morning, I thought, well, actually, if we want to talk about this in terms of sensor networks, it's actually infrastructural. And what I mean by both of these is that there are ways in which inequality operates that are sort of embedded in everyday cultures and society structures and practices, right? And we know this. We know that inequality operates in terms of income inequality, and that could be spatial and social, but it's structural in the sense that the family that you are born into and their characteristics is going to determine, to a large extent, the trajectory that you're going to face for the rest of your life, just as an example. But this holds, of course, in terms of racial or ethnic inequalities and racisms and the ways in which our institutions have been constructed to keep particular groups of people in particular parts of our sort of social structure, right? And of course, gender. And I wanted to give an aspatial example. And so the one that I sort of settled on is one that comes from the Opportunity Insights project from Harvard, which has fantastic spatial data and has done lots on sort of neighborhood effects and the importance of contextual factors in determining outcomes for individuals, especially children. But one really interesting aspect of this project is that they are not only able to place people and households in place, but also to link generations. And so they've done a lot of research that's really helped to show that there are these sort of structural factors in place that operate at the family level, but also sort of at the societal level. And so this graph is showing you the share of children that earn more than your parents by year of birth. And of course, the main takeaway in the US case is that over time, the share has been falling precipitously. And, about half of children born today can expect to make more than their parents, which I think if we're talking about sort of progress and measures of economic well-being, is a fairly dissatisfactory outcome to be seeing. Sorry, I've got a baby that's periodically talking behind me, and so part of my brain is on what's happening in the rest of my household, but hopefully this is working for everyone. Inequality, of course, is also spatial, and I don't need to tell anyone here about that. But just to provide a little bit more context, this is a map of England showing relative health and disability across England. And the real takeaway here is simply that there are clear geographic patterns and inequalities that exist simply in terms of the share of the population that is able or limited in their day-to-day activities, right? And so if you live in a particular place, you're more likely to encounter other people who are more limited in their day-to-day activities, but it also means that there are probably infrastructural factors at work that are determining both who is limited and how those limitations sort of play out in everyday quality of life and well-being, right? And then we know this also, this is an example of sort of digital exclusion taken from Newcastle in particular, where a lot of our case study work has been, just to show that, of course, even at the neighborhood scale, there are these differences that emerge in terms of who has access to different types of technologies and knowledge, but also who engages with those technologies and knowledge in different ways. And I think this in particular is very important when we start to think about smart cities and who benefits from smart cities. And then finally, inequality is process, right? And this to me seems like a really important element of what we think about when we think about bias and inequality and justice in a smart city context, that there are decisions that are made at various stages of sort of engagement with smart city technologies that embed inequalities, right? And this, for example, is when we decide what is important to fund. And this is both in terms of city budgets, but also in terms of research council budgets, right? When we decide that smart cities are more important than understanding, say, educational inequalities, and we shift funding in that direction, we inherently privilege some groups of people over other groups of people. Decisions about who is funding priorities are also important. So smart city technology, especially sensors, have been really important here because they're funded in different places by different groups. Sometimes it's corporations, sometimes it's cities making that investment, sometimes it's funding councils making that investment. And when that happens, of course, we're interested then in different groups benefiting or extracting value from these sensor networks. In almost every situation, I'm sure we're all aware of the sort of funding council context, but also the city budget context, that we're dealing with small pies, right? And sometimes pies that are getting smaller and smaller in terms of revenues, and we're having to allocate these scarce resources. And this process of allocation means that visibility and actual cold, hard funding are directed towards some groups more than others. And this will affect who has access to information. It affects analytical capacity at various scales, and it's going to affect how policy is developed. And it's within this context that I think thinking about sensor, there's one person I think who may not be muted. And if you don't mind sneezing while I'm talking, that's okay with me, but you might just want to mute yourself. And it's these processes in sort of a smart city context that I think are really important in thinking about inequality. Okay. Inequality is also inherent to technological change. This is not a new situation. This is something that has emerged at every stage over hundreds and probably even thousands of years, that as new innovations emerge, some groups benefit more quickly than other groups, and some groups are excluded more than other groups. I think that an argument could be made that when we talk about new smart city technologies or urban analytic technologies, so sources of data, that we have a very acute awareness of inequality and injustice, but that this tends to be aspatial, even when the research is coming from geographers and planners and urban analytics folks, right? And what I mean is that we have a sense that we know that at the sort of broader aspatial scale, we're going to get polarization and division. And we also know that cities are sort of internally differentiated, and that allows us to say that we believe that some groups are benefiting while others are not. But there hasn't necessarily been a lot of research actually on the ground to show where people are benefiting, so sort of literally within the neighborhood landscape, where people are benefiting and where people are not, and who those people might be. And so that's part of where we would like to make a contribution with this project. Okay. So the sort of overarching goal of the entire project has been ways in which we could support decision-making where sensor placement is concerned. So if we acknowledge that we're sort of up against a range of inequalities, right? Structural, infrastructural, but also in terms of process, what are the ways in which we could sort of insert ourselves along this decision-making process to, at a minimum, make sensor placement more transparent, but ideally actually aid with the ex post facto decision about where to place sensors in order to reach some sort of societal coverage goal across the city landscape. So that's sort of really what the heart of the project is about. Okay, and that's mostly what I'm going to talk about today. And one conclusion that we've come to in thinking about this, aside from sort of like how to decide where to place sensors, is just that making good decisions is really difficult. You have competing coverage goals, right? And so coverage itself is an incredibly complicated term, both methodologically, but I think conceptually as well. What does it mean to be covered by a sensor within a neighborhood or a city? And not everyone's going to agree what those coverage goals should be. Sensors are expensive at the moment, especially really good high quality sensors, which means that you can't simply place a sensor on every lamppost in a city, right? You have to choose, you have to make decisions, and there are going to be trade-offs. We also face the issue that, of course, and this reflects more my personal research interests, that we face demographic change and spatial sorting across the urban landscape. So different types of people tend to live in different parts of the city. And then finally, I think there's this sort of inherent tension, especially when we use the term smart cities, this tension between policy and data generation and sort of understanding and improving quality of life for those living in the city. And also this visibility and representation question, which is not really about data so much as saying we are a city which is engaging with cutting edge urban technologies to generate data, and then making sure that those who live in the city feel that they're being represented in this way that a city presents itself, right? Can people walk down their local streets and see that these technologies are sort of at play in a positive way in their neighborhood? And I used to talk a little bit more about sort of trade-offs between surveillance and sensor technologies for good. And I'm happy to talk about that after this presentation, but I'm really talking here about the types of sensors that are collecting information that would sort of benefit the individuals living in cities. So air quality sensors, for example, which is what I'll be talking about today. And so we've landed on this sort of idea of a sensor desert, right? Parts of the city that lack coverage. And we see these as parts of the city that are not represented by sensor networks, although representation, as I said, is a difficult concept to get a handle on. But you could think about this as parts of the city for which knowledge is not produced. So if we think about air quality, these would be, when we talk about air quality being poor or good in a city, and we've placed our sensors in selected locations, we aren't really saying something about air quality across the city. We're saying something about air quality for the locations in which we have chosen to place sensors. And that, similar to other environmental justice challenges, sensor networks present us with this issue that we simply may choose not to know what is happening in a particular part of a city. Could also think of a sensor desert, though, as areas in which the uncertainty of our estimates is higher, right? So of course, point-based sensors are only going to be valid for very small areas around those sensors. But you could think about this as sort of a surface, and you know that your estimate for air quality, for example, the further away you are from all sensors is the more uncertain it is, right? The less sure we are about whatever estimate we've come up with for air quality in that location. And so you could argue that people who live in places where uncertainty estimates are really broad are located in a sensor desert. We don't really have good hard knowledge of what air quality might be for those locations. All right. We've also sort of made an effort to sort of, especially in interfacing with engineers on the project, to differentiate between what we as sort of human geographers tend to think about as vulnerability oriented network purposes, making sure that you've got coverage for people, versus maybe a more engineering oriented perspective, which is hazard oriented, right? You want to place your sensors in the locations where the hazards or nuisances are being produced, for example, sources of pollution. So this is, of course, another trade-off that has to be made in deciding where to place a sensor within a city. Do you only place your limited number of sensors where the sources of pollution are, or do you place them where you think the populations at risk of poor air quality are, for example? But there's also thinking about how coverage in deserts sort of how they're important to different constituencies, right? And so one is simply political, the sort of visibility and representation question that neighborhoods or wards or portions of the city that lack sensors lack representation. It's not just about the data being generated for those parts of the city, it's about those parts of the city not counting politically or socially, right? This is process inequality. And this is, I think, in almost sort of, it's almost orthogonal to thinking about utilitarian or technical types of measurement, where if you can agree on what it means to provide coverage or what a footprint is for a sensor, right, or how your model is being estimated, then it's very easy sort of methodologically to tell which locations are falling outside sensor catchment areas. And so there's a lot going on when we think about sensor networks and what purpose they're actually serving within the urban landscape. I think that's sort of the main point that I want to make, and that deciding where to place those sensors is going to be really difficult for decision makers, because they're facing sort of this lots and lots of competing goals, right, that they have to weigh, and that I think a lot of these decisions are being made implicitly. When you decide to place a sensor in a particular location, you have a fixed number of sensors. Implicitly, there's a lot of weighing of different goals and needs of different groups, and these aren't necessarily made transparent or made explicit. And so what we could use are tools that at least help decision makers walk through this process in order to understand what happens when decisions are made in a particular way, and then be able very quickly to see what happens if you move sensors around, how coverage might change or change your priorities. Okay, so what we've been working on are tools that help visualize and work through these trade-offs and outcomes. As I said, ideally before sensors are located. I think that's probably a stretch given how decisions are made to locate sensors. But I think the transparency piece, the working through trade-offs, sort of a worksheet and set of tick boxes that sort of make it clear on the map what happens to coverage when different numbers of sensors are chosen or when locations are moved, those tools would be really useful for decision makers and lots of different constituencies. So this was a very early prototype of this decision support tool. And I just want to point out that there are a few different things happening, right? So at a minimum, you want to weigh through the different types of trade-offs that have to be made. And these have to do with costs of sensors and therefore how many sensors you can afford as the person locating the sensors, but also what the priorities are going to be in terms of placement. Right? Is it different demographics, different age groups? Is it source versus vulnerability? Are we favoring where people are at night or during the day? What are we thinking about in terms of coverage, right? And sort of that sort of footprint or catchment area for an individual sensor. And this there's a sort of true but unknown catchment area for individual sensors that is highly dependent on the local built environment and sort of broader weather patterns. But the way we've thought about coverage is that the sort of the bandwidth that you set around coverage gets at this sort of representation and visibility, right? In which you can have a broader coverage area, say 0.5 kilometer here, where really you're just saying, do you have a sensor in your neighborhood, right? Are you covered politically? Versus sort of smaller coverage footprints, which are really getting at for which parts of the city do we think we're providing accurate air quality measurements. So how do we measure coverage? Well, so I should go back a little bit just to say that this interface, of course, has the front piece, right? The front end with which individuals and groups are engaging. And there's sort of lots of testing and interaction happening on that side. But then underneath it, there has to be some sort of process by which you decide how many and where to place the sensors and then estimate the coverage, right? So we have two different pieces of work going on here. And so here, and mostly what I'm going to talk about for the rest of the talk is really how we measure coverage, right? And so the approach that we've taken is really an optimization approach, right? The best allocation of a given set of sensors given a particular goal. Right. And we use two approaches. So I'll talk about both a little bit. One is just a single objective algorithm that places our sensors one by one and is maximizing coverage for one subgroup. So for example, you have a given number of sensors that you would like to place in the city, and you'd like to maximize coverage of children, right? The algorithm will then place the sensors such that you are covering the largest number of children possible. But that, of course, is going to leave all other subgroups off the table. Right. So we also use a multi-objective genetic algorithm that creates lots and lots and lots of networks, right? And then allows us to sort of choose across sets of networks that basically are giving us good or sufficient coverage across a set of dimensions. So lots of different demographic groups, for example, right? Coverage for us is going to be this sort of bandwidth, right? And we've worked with sort of two different sets of bandwidths. The larger, the sort of 0.5 kilometer bandwidth, is going to cover output areas, which are sort of basic geographic units of analysis, and then sort of fractions of surrounding populations, depending on the size of the output area. We place our sensors at output area centroids, which is not super realistic, but for smaller output areas, and these can be really geographically quite small areas, probably isn't making so much of a difference. But for sort of larger output areas where population density is lower, we're just making an assumption that this is the place that we would place the sensor. Okay, we're working with the Urban Observatory in Newcastle. So this is the UK's largest air quality monitoring network. They actually have lots of different types of sensors on lots of different dimensions, and they stream a lot of real-time data. So this has been a pretty big funding council investment. And you're free to have a look to the data. Sort of our starting point with this project was, here's an observatory, a smart city sensor network that is already existing, for which sensors have already been placed. What can we say about the coverage for those sensors, and how might we sort of rejig sensor locations if we were hoping to optimize or improve coverage on any smaller set of sort of demographic dimensions, right? So a lot of the analysis has turned out to be sort of independent of what the Urban Observatory is doing, but of course, because they do already exist in the Newcastle landscape, they provide us a point of comparison. Could we do better than really careful, well-experienced engineers who really care about smart cities and sensor networks? Could we improve on sort of the status quo? This is sort of what their interface looks like. So at any time you can go in and look at the different types of sensors, which are everything, as I said, from air quality, but also including water quality, noise, traffic. And the sensors that we're working with across all of Tyne and Wear, which is the larger region within which Newcastle is situated. It's almost 200 sensors within Newcastle. It was 144 when we started this project, and is now 146. So this project has been going on long enough that they're a little bit of a moving target. And this is where they're located within the city of Newcastle. And so I think even a naive observer would say, they're clearly not uniformly distributed, these air quality sensors across Newcastle. There do appear to be clusters of sensors. And sort of an initial question may be, well, who are the people, or what are the other urban characteristics of the parts of the city where these sensors are located? And as you might guess, the sensors, sort of this, if you can see my cursor, but that the larger cluster of sensors is indeed in the city center, right? So where it's highly trafficked, both in terms of sort of hazard production, but also sort of movements of people. But there are these other areas of the city, right? There's a sort of secondary cluster. And this actually, it turns out, is in a fairly well-to-do part of the city. So if we were to compare, and I don't think that I show any of this today, but if you sort of compare the demographics of where the sensors are located, the most deprived areas of Newcastle really have almost no sensor coverage whatsoever, whereas the more middle class, well-to-do parts of the city are fairly well covered with existing sensors. Right? So could we do better with this if we were hoping to maximize coverage of, say, elderly people or young people? Right. So this is just one example of a network, 50 sensors, aiming to maximize coverage of the total population, right? And so with 50 sensors, and I think our bandwidth is at 0.5 kilometer here, but really this is just an illustration of where the sensor deserts are. So these sort of lighter colored areas, lighter colored parts of the city are parts of the city where there would be no coverage. This is very different though, just to sort of, this is only 50 sensors, but just to go back to what we have with the Urban Observatory, which is very clustered and probably has some redundancy, just by imposing the total population coverage goal, you force a certain uniformity of coverage. So in terms of representation, all right, if you want everyone in the city to be able to say that that the city cares about them, that it cares about their air quality, that city officials know something about their neighborhood, then simple optimization definitely, I think, provides an avenue for ensuring that this happens. All right. As we change the number of sensors, of course, coverage is going to improve, but we sort of top out pretty quickly. So at the top, so on the left panel, what you're seeing is networks that have 20 sensors versus networks that have 60 sensors on the right-hand panel. And on the top, we have the shorter or smaller coverage goal versus sort of a larger coverage goal on the bottom panel, right? So if we have 60 sensors in the bottom right, where our bandwidth is set at 0.5 kilometer, we cover about half of the population, right? And so, of course, in an ideal world, what you would want would be lots and lots of sensors, right? Because with lots and lots of sensors, you can saturate the city landscape. You can cover pretty much everywhere with a high degree of confidence. But this is not how it works in the real world typically, right? The tricky thing is that, so this is total population, right? And so you can sort of maximize coverage for total population. You could get half of the population with just 60 sensors. And remember, the Urban Observatory is funded, well over 100 sensors. So we could definitely push that up further. The tricky thing is that people sort over space, right? So in the upper left-hand panel, we have the total population, right? So you have city center where there aren't as many people living, but then sort of higher densities immediately surrounding the city center, and then decreasing population density as you sort of move out further from the city center. Workplace populations in the bottom right-hand panel, those are highly centralized, which isn't so surprising. So it's relatively easy to get good coverage of workplace populations with fewer sensors. Children and elderly, and these are the only subgroups I'm going to talk about today, but you can imagine the same might hold for ethnicity, for example, or income or deprivation, that these are they're located in different parts of the city. So if you decide that you would like to privilege coverage of children, for example, then a trade-off might be that you aren't really providing as good coverage for the elderly population or the workplace population, because children are located in very different locations from the daytime working population. All right, and people, of course, are also mobile. So the way we've captured this so far is just with the workplace population. But ideally, and when we started with the project, What we really wanted to capture were sort of the in transit between origin and destination. As people sort of pass within the coverage area of a sensor, can we capture them and say that we're collecting air quality information for these people as they're mobile throughout the day, right? So what we have right now is sort of static, sort of nighttime residential populations and then workplace population. But for workplace, as I sort of suggested just a couple of slides ago, we can get up to 80% of the population with just 60 sensors, right? Because the workplace population is in these very few work centers during the day. So the biggest tension is really between coverage for the workplace population and coverage for other demographic subgroups, right? So on the left, we have the elderly population, and on the right, this workplace population that I just showed you. And for the elderly population, because of the more dispersed nature of this population, but sort of the high vulnerability to poor air quality, you can see that with 60 sensors, we can cover about half of the population, but those sensors are located in mostly very different locations from where we would place our 60 workplace populations. So it's a choice between covering one group or the other. And on these top panels for both, we've set the bandwidth to 250 meters, which is probably it's a more realistic estimate of what the coverage would be for an air quality sensor and is already generous, right? In other words, the best estimates for these sensors are actually very close to the sensor. The 500 meter rather, is really about representation as opposed to high quality air quality measurements, right? Okay, so the trick is then whether we can identify compromised networks that might not be the best or optimal at covering any one subgroup, but are satisfactory across all of them, right? And so here we set our bandwidth to 500 meters. We have a 55 sensor network for reasons that I'll get into in just a little bit. And what you can see, these are 200 estimated networks. These are all of the dots set across these four categories. So total population, children, elderly, and workplace. And the blue dots are those networks that meet 45% coverage across all groups, right? So we get a number of networks. I mean, if 45% coverage is satisfactory to you, we can come up with a number of networks that will meet that criterion across all dimensions, right? And as you can see, we can get quite high with the workplace population, but the ones that are very best at covering the workplace population, they don't meet the other criteria, right? So you have to be willing to trade off, take a little bit less coverage for the workplace population in order to get higher levels of coverage for the elderly and the children and the total population. Right, so this is an example of a 55 network solution at 0.5 kilometer. And we get coverage of about half of the population across all of these categories. So half of the total population, but also half of the workplace population and almost half of the children and the elderly. What you'll notice is that this is a fairly dispersed air quality sensor network, right? So it looks a lot different from what the Urban Observatory Network looked like. And you might argue that half of any one of these groups isn't optimal. But if you think about what the Urban Observatory Network looked like, it's clear that there's no way that they're covering lots of different subgroups. So what we did was ask ourselves, what would happen if we compared our approach to this actually existing network of the Urban Observatory? So there are these 146 Urban Observatory sensors at the moment. They're located, though, in 55 output areas. So what we do is we snap those sensors to the output areas so that we're comparing like for like. So if the Urban Observatory had placed their sensors at the centroid of the output areas in which they're located, what would their coverage look like, right? And then we estimate coverage in the same way. So again, with the bandwidth of 0.5 kilometer, this is what coverage would look like for the Urban Observatory. So it's about a third of the youth and elderly populations. It's just over half of the workplace population, and it's just over a third of the total population. So much more clustered, much more condensed coverage relative to our approach. It does cover the city center well, but you can see that it's sort of, yeah, there are lots of parts of the city, and traditionally these areas along the river, so the sort of dark line running at the bottom of the map, these have been some of the most deprived neighborhoods, not only in Newcastle, but in the country. And there's really a paucity of sort of sensor placement in those parts of the city, right? So our approach sort of forces that coverage to be a little bit more representative. And so we asked then ourselves sort of, where do we get sort of over coverage and under coverage, right? If we were to take this investment from the urban observatory and pick up those sensors and maybe move them to other areas, right? Where might that be? And so the orange areas on these maps, and this is total population, children, elderly, and workers. The orange areas are those that are underserved by the existing urban observatory network, right? And so you get these areas along the city, but you also get some other outlying areas throughout Newcastle for workers, but also for children and for the elderly. So you can see this, especially for these sort of demographic subgroups like children and the elderly. There are really lots of parts of the city that are arguably underserved by the existing network. And the purple areas then would be those that are sort of overserved, right? Where you just have this redundancy of sensors. Lots and lots of sensors have been placed in, I mean, from a demographic perspective or representation perspective, essentially exactly the same location, right? From an air quality or sort of hazard perspective, that argument isn't quite as straightforward. But from a demographic perspective, there are these purple areas, these parts of the city where you just have redundant coverage, right? And so if you look at the same plots, right? So here the horizontal line on this graph is showing the urban observatory coverage, right? So about a third, and then a little bit over a half, right? Then these blue networks are those that cover all. So we can well outperform the urban observatory where total population and children and elderly is concerned by taking this sort of optimization approach to sensor placement. Workplace population, because of that clustered nature and because so many of the urban observatory sensors are in the city center, the situation's a little bit different. Okay, so there are lots of next steps. I realize for a keynote that sort of funny to talk about work in progress, but partly because of pandemic and partly because it's always interesting to get feedback from expert audience members. I thought it's nice to talk about something where we aren't quite done and we're still sort of working through what we're doing. One is the sort of flexibility of the decision support tool. For example, if you look at these networks, right, you could imagine that a decision maker might place these sensors, look at the coverage along different dimensions and then say, well, what would happen if I were to move a few of these sensors into these other locations? Or what if there's an intersection that I really need to make sure is covered? What if I have to have sensors in this part of the city and then manually be able to move those sensors and then regenerate the estimated coverage? That piece of sort of manually moving sensors and then re-estimating coverage, that I think is a really useful part of thinking about decision support. It makes those trade-offs really explicit and allows decision makers sort of in real time to play with hypothetical situations and numbers of sensors. So that's something that we really feel like we would like to have in the final decision support tool. We're also working still on the optimization portion of the project. This is very bespoke at the moment. It works really well for Newcastle and for Gateshead, but ideally the sort of optimization routines you'd be able to pick up and apply certainly anywhere in the UK, but ideally sort of agnostic to local context if you had the appropriate data, right? So that anyone could employ this package to estimate sensor networks. Decision support means asking people how they're engaging with tools and testing. And so there's some of this that we've done, but there's still lots more to come to make sure that we're building something that is actually useful and intuitive to the people that we envision making use of it. And then we're still sort of wrestling with this differentiation between sort of vulnerability and hazards. And that we really would like to be able to incorporate some aspect of hazard source, pollution source, in the decision support tool that would allow users to toggle between privileging or weighting the demographic aspect, right? Who lives where, against the sort of where air pollution is being produced, which is largely traffic-based, right? And so we've been thinking a lot about how to estimate traffic flows and therefore local air pollution. And one thing that we've been exploring would be just using space syntax as a proxy for what we think traffic and air quality would be. And so that's something we're exploring. We'd be really interested to hear comments from the audience. This is sort of one of our key next steps. Yeah, and so just some final takeaways that, this decision making, I think the ways in which decisions are made about where to place technologies isn't a large part of our conversation. When we talk about smart city technologies, we tend to focus on what we do with the data, right? Without sort of necessarily taking a step back and asking something about the sort of data production process, right? And what that means for who's covered, who's not covered, what should be measured, how it should be measured, and where. And that comes with uncertainty, but also comes with lots of trade-offs. And so we're really hoping to help illustrate those trade-offs and at least help make the decision-making process more transparent. And that there are a lot of challenges to spatial inequality and unevenness. And we know this. We talk so much about bias and inequality when we talk about urban analytics or smart cities, but sort of how we get at that on the ground and remediate it, if it can be remediated. I think that's sort of an interesting avenue of research. And then finally, sort of one that we've been tackling for a long time, like from the very inception of the project, is what we mean when what do we talk about when we talk about coverage and production of knowledge, right? That we had lots of interesting conversations about coverage areas for a sensor and what a sensor desert might look like. And it turns out that this is challenging methodologically, as I think you've probably seen, but it's also really challenging conceptually because it means different things to different people. And it's possible to have two types of coverage at work at the same time. That is, it's possible for a sensor to be in a neighborhood and providing accurate, mostly air quality measurements for a very small sort of area or catchment area, and for that still not to mean that the larger neighborhood is feeling represented in the sort of larger sort of process of political process, I guess, or sort of social process across sort of city hierarchies. And I find that really interesting and something that I think we've really enjoyed talking about in this project. And I think with that, I will stop. And I don't know if I should stop sharing or.
Can you hear me, Rachel? I think you can now. You can leave the presentation on just to help, perhaps going back to some slide if someone has a question. I've seen some questions in the chat with even the particularity of the Newcastle, so it's good to go back to it. So I'll open the floor to questions. I have some questions myself, but I'll leave the audience to start. We'll start with Alan, who wrote already in the chat that, can you see the? Yeah.
Yes, I can see. So, yes. So this is a really interesting. This is an interesting question and one that we get a lot. So, when we have asked engineers, and now I'm talking about the Urban Observatory, when we've asked them about how they decided to place sensors, the answer that we get, in short, is it was an ad hoc process. And this has to do with the fact that it's really that there's a lot going on. So first of all, you can't just go place a sensor wherever you would like, right? So this is where the Urban Observatory, because they are actually out on the ground, has an advantage over us. You certainly can't place them at geometric centroids necessarily, right? But you also just can't place them anywhere. You have to have the rights not only to place the sensor, and some of them, the higher quality ones, are still quite big, expensive pieces of equipment. You not only have to have the right to sort of hang that in a particular location, but you have to have the right to maintenance. So people have to have the right to come back and check on the sensor repeatedly. So that's already a constraint that we don't or haven't yet really attacked in this decision support tool. There are a couple of other challenges. The other is that some groups tend to advocate and talk more loudly about needing to know what their air quality is versus other groups. And so the squeaky wheels, as we would say in American English anyway, they tend to get the grease, right? And so that's one reason why a lot of the sensors are located in fairly well-to-do neighborhoods, because those places have really articulated that they want to know what their air quality is. It also happens that in Newcastle, and this is unusual in cities, I think, that you have an interface of sort of high socioeconomic status and poor air quality, right? So some of the worst air quality is in some of the richest parts of the city. And so they have really been able to articulate a need to have sensors in their neighborhood. And other groups in the more deprived areas who also have poor air quality, they haven't done that. So that helped guide where sensors were located. And then the third factor was that, and this is again sort of a spatial demography challenge, is that these sensors, because they're expensive, they're treated differently in different parts of the city. So in some parts of the city, they're destroyed very quickly. And that means that you might locate a sensor once, but you're not going to locate a sensor twice, right? Because it's just foolish. So that leaves some parts of the city that are maybe a little bit more deprived, relatively uncovered in terms of sensor placement. So that sort of, I think, explains a lot. Oh, and the third is that they are much more hazard focused than we have been. We're much more people focused and vulnerability focused. And that means that we've sort of purposefully placed sensors where people are, because we want to know something about who's exposed to poor air quality. Whereas they're much more focused on where the heavily used intersections are, where congestion is located. And so that means that a lot of the sensors are in the city center. Hopefully that answers the question. Yeah, so winds, so we don't actually do any, so I think this is part of a bigger question. This is another question also from Alain, who says, who asks if I've considered dominant winds from the sea in Newcastle and their impact on sort of the buffer of air. And this gets at what actual air quality is versus what we would be estimating. And it turns out that modeling air quality at a very high spatial resolution is really difficult, because you've got these sort of wind patterns, but you've also got the built environment, right? And these sort of canyon effects of where air moves and where air stays, especially sort of poor air quality. And we don't deal with that at all. The way we've thought about it is not in terms of what we would use for bandwidth or how that bandwidth might be shaped, but rather if we pursue sort of uncertainty as a way of thinking about deserts, then it would be taking the product of the air quality modeling and looking at the parts of the city that have relatively wide uncertainty measures, if that makes sense. So if we're not really sure what your air quality is, given wind patterns, given the built environment, given the inputs to the model, if we don't really know where your air quality is, then you live in a sensor desert, because we should be able to say within a fairly narrow, I'm using bandwidth in lots of different ways here, but the uncertainty measurement should be relatively narrow. And where it gets too broad, then we would say that's a desert, if that makes sense. But we haven't really worked with we're not doing any air quality modeling on our own in this project. Okay, I've got lots of questions.
I'll help you with one of them.
So Denise asks about spatial inequalities in air quality. Yeah, so this is the hazard piece, right? So if you're thinking about where to place sensors, do you place them where you think the air quality is really poor? Or do you place them where you think the people who are vulnerable to air quality are? And of course, it's the two, right? It's that, people with poor health, for example, you need to know what their exposure is to poor air quality. And you also need to know where those hazards are located. So I think this is why our feeling is that the decision support tool needs to allow decision makers to incorporate both, right? Because in reality, both are important. It's just much more difficult to get at the hazards piece without using something that's already estimated, right? because most of the air quality is already an estimate. So you're sort of building in the artifacts of whatever bias were already in the model, and then you sort of carry them through. So we're looking for ways that we can sort of get around the hardwired bias that's in models without having to go back into our own modeling. And maybe it's not possible. But that's sort of where our thinking is about air quality. But yes, that's definitely a factor. Richard Kingston asks, in Manchester, through our urban observatory, we found that the cost of the sensors was not a barrier to potentially having them very widespread across the urban area. The biggest barrier and costly part was the company contracted by the city council, the owner of the lampposts, to fix the sensors to lampposts. I think that this was part of the sort of initial location problem also in Newcastle that I talked about earlier. Yeah, it just turns out that it's very tricky to be able to place the sensors where you want. Although some of these sensors are quite expensive, right? So the urban observatories benefit from Research Council funding to invest in these sensors, but that's not the only avenue by which cities place sensors, right? Sometimes it's also done through a piece of the city budget. And in those cases, you know, every allocation for an additional sensor is money that's diverted from some other part of the budget. So I think there are these trade-offs about the cost of the sensors, but that's a very good lead into Jeffrey Caruso's point, which is about mobile sensors. All right. So it's been interesting to me over the 3 years that I've been thinking about this a lot, that I think the conversation is just moving really quickly about sensors, right? I think we're past the point of these big boxes or smaller boxes that are placed in a static location. We're past the point of that being sort of the cutting edge of smart city technologies, because we already sort of move into sort of having cheaper sensors that also provide valuable information and valid information, but also just, it's probably just a small number of years before we can sort of carry our sensors around with us and have a reasonable estimate of what the air quality is as we move through space, right? The thing about the sensor networks that I think is important is that one argument that's made for air quality sensor networks in particular is sort of for policy evaluation and impact, where, if you impose congestion charging, or if you close a road that is heavily congested and is producing a lot of air quality, what will happen then? And that means that you have to have a before and you have to have the after. And so, I think mobile sensors can fit that purpose, but there's a research design challenge that I'm not sure that the research design challenge has actually been met with static sensor networks, but I think it's a really important part of the conversation that isn't really talked about, right? That what you need is to have in place sensor networks across the urban fabric such that an unanticipated shock and its effects can still be measured afterwards, right? So you need to be able to have the before, and then you need to be able to have the after. And that requires a certain, I think, spatial array of sensors, because you don't necessarily know what those, that's the nature of the unanticipated shock, right? You don't know what that shock is going to be and where it's going to be felt. So I think in my mind, that means that the sort of static sensor networks still, if they are to be used for policy, then they still have a really important role to play in cities. Yeah.
Good. More questions from the audience? Anyone wants to open the mic and ask the question live? Because I have a couple of questions. I'm leaving myself to the end.
Maybe if I can just come a little to go on what Rachel just said. Maybe there is an in between where it's actually the community that pays for, I don't know, a truck to move basically those sensors, every other week, or so it's kind of a sampling across space and time. It's not necessarily portable. I understand. I see the issue of portability, but maybe there's in between that is. Then we see that you don't need to maybe concentrate so much, and by sampling across time, I'm sure most of the data is very similar day to day, and somehow it's a loss of investment as well to keep the things in the same place all the time. Those sensors
So there was Yeah, so there was one component of the Newcastle Urban Observatory was a project that was called Sense My Street, which was a sort of an interface that allowed community groups and citizen groups to request sensors and then would provide training. So it was a little bit of citizen science, a little bit of sort of participatory science. And one thing that became clear there was that there's only certain neighborhoods that were going to take advantage of that, but also just have the capacity to self-organize within their neighborhoods. And so, yeah, somehow, I agree with you about the mobileness, but I think sort of bottom up, we haven't solved that problem of bottom up. That top down science still remains really important because of the process inequalities that are embedded in sort of citizen science or, participatory anything. Some people are more able and willing to participate than others. And just because they can't doesn't mean that their part of the city shouldn't benefit from, especially something so straightforward as knowledge about the air quality in a neighborhood.
Good. So I'll follow up with the first of my questions to Rachel. What is the moment, I think you haven't factored that in your modeling, but what is the moment in which you say, I have a sufficiently widespread network of sensors, I can interpolate between them, guaranteeing that other people that are not in catchment areas, but they have good interpolation values on the real time. Of course, there are computational costs, etc. But have you thought about that?
Yes, but that's sort of like would be next step after this decision support tool. That's the uncertainty piece, right? That's the, could we, maybe it doesn't matter if you have a sensor nearby, as long as the estimates from the models that use those data as inputs, as long as those are valid isn't the word that I want to use, but as long as they give us reasonably sure information for every part of the city, right? And so I think what we've decided there is that we just don't have the capacity. We weren't designed, our team was not designed in any way to do air quality modeling. And it turns out to be really, really complicated, that it's easier to partner with people doing the air quality modeling and then work with them to sort of look at, ideal size of networks, but also where sensors need to be placed. I mean, I have a residual feeling about this, which is if it doesn't really matter whether or not you have a sensor in your neighborhood, because the air quality models are going to account for this, then why aren't all the sensors in the poorer neighborhoods? Right? And until the sensors are actually in poorer or more deprived neighborhoods, I don't really buy the argument that it doesn't matter, because the air quality models will pick it up. If air quality models really would satisfy all groups, then we shouldn't be able to predict which types of neighborhoods are going to benefit from sensors. If that makes, and I'm not sure if that makes sense, but if I can predict whether or not you have a sensor based on your neighborhood characteristics, I think that that's a problem.
I agree with you. I was assuming that we would put, or your project would put some sensors in the private neighborhood anyway, but it would provide at the same time a layer of estimation that is sufficiently that everyone will be catered for, and not the estimates based on I
think we have two parallel streams of research where the air quality piece and sensors are concerned. You've got the statisticians and climate scientists, urban scientists working on the models for air quality, and then you have people thinking about sensors and where they should go. And actually, there needs to be tighter integration between these two streams of research. I completely agree.
And that leads to my second question, which is: have you come across other research or in the industry? So I don't know, cell phone companies and where they locate their own antennas and other infrastructure, or the big tech like Cisco or whoever populates sensors across cities in city packs or cities. Do they have research or engineering or knowledge on this kind of thing that you could pick up and apply to your?
Yeah. That's a really good question. I hadn't even thought about the cell phone or mobile phone companies, but that's a really good point. We haven't come across anything. I mean, if you look around and you sort of compare the decision-making process for where to place sensors, there's quite some variation. And I would say there are plenty of cities that have made an explicit decision to have uniform coverage, right? That you start, first you place a sensor in every neighborhood, and then you additionally place other sensors on other criteria, but everyone gets to have a sensor. That's not an uncommon approach to sensor placement. Yeah, so I think it really depends on sort of who's making those initial decisions.
We back in the chat, we have Alain again saying that he has colleagues that developed in different departments, probably engineering and electronics or whatever, air quality nanocaptors, so chip that could be put virtually everywhere, but still in the lab, not yet for sale. Have to wait for a bit more time. And the second comment is, what other types of sensors networks could benefit from such social spatial approach? Yeah.
Right. So on the first point, I think we live in really exciting times, right? Because the science is moving quickly. And maybe most of us here in this conference, we think about the methods and the data moving quickly, but actually the technology is moving quickly also, of course. So I think it's exciting to see sort of how that advances. Other types of sensor networks. Well, I mentioned this at the beginning of my talk, that one of the common comments that we get on this research is that we're assuming that coverage is a good thing. So you could take the inverse, right? I think for lots of types of sensor networks, actually being in a desert is a privilege, right? Where do you get to live where the state does not collect information about you, right? And that could be CCTV, noise, these sort of other ways in which some populations, so this, this sort of research on sensors tends to sort of follow a surveillance, tends to focus on surveillance, which I think is valid. So I think you could take the inverse of our approach and ask who gets to live in deserts for a lot of different types of sensor networks, and that would also be interesting. I mean, I'm not pro surveillance, but I also think you shouldn't be able to predict who is surveilled, right, based on their characteristics. If it's going to happen, then we all have to be watched, not just some of us.
Yeah, that's a good discussion, isn't it? We just heard about some country that is now predicting crime based on street survey. So it's kind of, what's the name of the sci-fi movie? Minority Report kind of prediction of who's committing a crime. More questions from the audience? Okay.